TCI Weather, Lesson 4, the introduction. Air pressure and wind. You cannot see it, but you can feel it. What is wind and what makes it blow? Introduction. On the day this photo was taken, the tall grasses were waving back and forth and the blades on the wind turbines in the distance were spinning. Of course, you know the cause is wind. But what is wind and what causes it to blow? Why is wind strong enough to turn huge wind turbine blades one day when it barely rustles the tall grass on other days? Air is matter and wind is air in motion. Because air is matter, it has weight and can make objects move. When something is not heavy, people say it is as light as air, like the air has no weight at all. But the weight of air can be measured. The atmosphere contains an enormous amount of air and pushes down on the ground with a great force. You have already learned about temperature, and now you explore one of the important relationships in weather between atmospheric pressure and wind. You will learn how atmospheric pressure varies with altitude, how it is measured, and how changes in it cause wind. You will explore how wind interacts with other parts of the Earth system and how it is involved in the flow of energy. You will conclude by finding out how engineers design hang gliders so that people can soar on the winds. Section 1, Atmospheric Pressure. Air can affect the shape of things. How? A bike tire feels squishy when it goes flat because it does not have enough air in it. You have to pump it full of air to make it firm again. So how does adding air to a bike tire help it keep its shape? Pumping air into a bike tire increases the pressure inside the tire. Pressure is a force applied to a certain area, with force being any push or pull. The girl pushing down on the pump in the photo is exerting a force on the handle of the pump. The particles in the air also push on the inside of the tire when they bump into the sides of the air tube. As more air is pumped into the tire, more particles bump into the tube sides, increasing the pressure of the air inside the tire. That makes sense. The pressure of the air inside the tire is not the whole story, though, behind why bike tires need to be filled with air. The air outside of the tire is also pushing against the outside walls of the tire. In fact, all of the air in the atmosphere above the tire is pressing down on the tire. Air may be very light, but there are many kilometers of air above the bike tire as well as above you. Earth's gravity pulls on all of this air, giving it weight. Atmospheric pressure is the weight of the air pushing down on an area and is also measured in millibars, MB. It pushes down on you, the bike, the ground under the bike, and everything else on Earth. Pressure increases as the density of the air increases. Density is a property of matter that is equal to the amount of mass in a certain volume of matter. For air, density depends on the number of particles that are in a given volume. You can use the model in Figure 1a to explain this relationship. The model on the left represents air at sea level, while the one on the right represents air at the top of Mount Whitney. I'll show you those in just a second. Notice that there are more particles in the same volume of air at sea level than on the top of the mountains. The models show that air is less dense at higher altitudes than at lower altitudes. As a result, atmospheric pressure is also lower at higher altitudes than at low altitudes. The density of air depends on altitude. At sea level, at 0 kilometers, at 0 feet, that circle represents the amount of air molecules in a very small drop, a little bit of air. Look at all the molecules. But then on the right at the top of Mount Whitney, 4.4 kilometers, 14,000 feet, there's not as much air. That's why people have to wear oxygen when they climb to the top of mountains. Figure 1a. These particle models shown in the circles compare the density of equal volumes of air at sea level and at the top of Mount Whitney in California. The air is less dense on the top of the mountain because it contains fewer particles there than at sea level. The density of air in the atmosphere decreases as altitude increases because gravity pulls air downward. The density of air depends on the altitude because gases are highly compressible. This means that air's volume will shrink when you press on it. In the atmosphere, air Air presses down on the air below it. Think of a tall stack of pancakes. The pancake on the top will be the fluffiest because no other pancakes are pressing down on it. The pancake on the bottom will be a bit squished because the weight on all the pancakes is pressing down on it. As a result, that bottom pancake will be a little bit denser than the pancakes above it. Just like the bottom pancake, the air at the bottom of the troposphere is compressed by all the air above it. Therefore, air is more dense at sea level. Sea level is the elevation of the land surface where the atmosphere meets the ocean. It is the starting point for altitude measurements at 0 kilometers. Some places on land, such as New Orleans, Louisiana, are a few meters below sea level. Others, such as the top of Mount Whitney, California, are more than a kilometer above sea level. Therefore, the density of air in New Orleans is greater than the density of the air on top of Mount Whitney. Atmospheric pressure decreases as altitude increases. This is because the density of air decreases the higher you go. The graph in figure 1b, the one right over here to the right, shows this. At sea level, such as the shoreline of San Francisco, California, the atmospheric pressure is 1,013 millibars. In Denver, Colorado, at about 1.6 kilometers above sea level, about a mile, it's called the Mile High City, atmospheric pressure is 840 millibars. At the top of Mount Whitney and at about 4.4 kilometers above sea level, the atmospheric pressure is about 600 millibars. At 10 kilometers above sea level, the top of the troposphere in some places, atmospheric pressure is only about 260 millibars. Did you notice how much lower the density of air is at 10 kilometers than at sea level? This explains why commercial aircraft cabins must be pressurized. Thus, there is a cause and effect relationship between altitude and atmospheric pressure. A cause and effect relationship is a connection between events in which one event is caused by another event. When altitude increases, atmospheric pressure decreases. This relationship can help you predict how atmospheric pressure will vary from place to place in the world.